Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving deep into a fascinating topic, reasoning by superposition, a perspective on chain of continuous thought. This is something I've been pondering a lot lately, especially considering the advancements and limitations we're seeing in AI.
Yeah, I'm really excited about this one. The idea of a continuous chain of thought, especially in relation to how we might achieve AGI, is something I find incredibly compelling.
I'm intrigued, but also a little skeptical. The phrase reasoning by superposition sounds almost mystical. I'm hoping we can ground this in some concrete examples and talk about how it differs from what current AI, especially deep learning, is doing.
I agree, Sarah. It sounds a bit like hand-waving at first. I'm particularly interested in understanding how we can translate this idea into something that's actually implementable, something that addresses the spatiotemporal challenges I see in current AI systems.
Okay, so let's start with the basics. What do we even mean by reasoning by superposition in this context? The way I see it, it's about moving beyond the idea of thought as a linear, sequential process. Instead, imagine the brain holding multiple possibilities, multiple hypotheses, multiple perspectives, all active simultaneously.
Like parallel processing on steroids. So instead of A, then B, then C, we're talking A and B and C, all contributing to the final decision or conclusion.
Exactly. And not just contributing, but interacting, influencing each other, competing, combining. It's a much more dynamic and fluid picture than the step-by-step reasoning we often program into AI.
Okay, I see where you're going. But how does this differ from, say, the way a neural network already works? Don't different layers of a network activate in parallel, processing different aspects of the input?
That's a good question. I think the key difference is in the nature of the representations. In a standard neural network, each neuron is basically performing a weighted sum of its inputs, followed by a nonlinearity. It's a statistical operation. Superposition, as we're talking about it, suggests something more symbolic, more structured, maybe?
Yes, and also the type of information that's being superposed. Think about a chess game. A traditional AI might evaluate each possible move sequentially. If I move my rook here, then my opponent might do this, then I might do that. It's a tree search. With superposition, the AI might hold multiple potential board states in its mind simultaneously, each representing a different strategic approach. It's not just evaluating them one at a time, but considering how they relate to each other.
And that's where the spatiotemporal aspect comes in, right? It's not just about the current board state, but also about the history of the game and the potential future trajectories. To really superpose those possibilities, you need a way to represent and manipulate them in a shared space, a shared time frame.
Okay, the chess example is helpful, but it still feels a bit abstract. Can we think of a more concrete, real-world example where this kind of superposition is clearly beneficial, maybe even necessary?
Well, think about driving a car. You're not just reacting to what's directly in front of you. You're anticipating what might happen. That pedestrian might step into the road. That car might change lanes. The light might turn red. You're constantly running these simulations in your head, superposing different possible futures and adjusting your actions accordingly.
Yes, and that anticipation isn't just based on simple pattern recognition. It's based on a model of the world, a model of how people and objects behave. You understand that pedestrians are unpredictable, that cars sometimes make sudden maneuvers, that traffic lights follow a certain pattern. That understanding informs your superposition of possibilities.
And that understanding is deeply rooted in your spatiotemporal experience. You've seen pedestrians step into the road before. You've seen cars change lanes. You know how long traffic lights typically stay green. All of that information is encoded in your brain and used to generate those anticipatory simulations.
So, if we were to build an AI driver using the superposition principle, how would it differ from a self-driving car that's based on current deep learning techniques?
The deep learning car is trained on massive amounts of data. It learns to recognize patterns. Pedestrians in this situation usually do this. Cars in that situation usually do that. It's very good at reacting to what it has seen before. But it struggles with novel situations that deviate significantly from its training data. That's where the superposition approach could potentially shine.
Exactly. A superposition-based AI driver could reason about the underlying causes of events, not just the correlations. It could understand that pedestrians step into the road because they want to cross it, that cars change lanes because they want to get ahead, that traffic lights are controlled by a timer. That understanding would allow it to anticipate events even in situations it hasn't encountered before.
and it could do it in a more computationally efficient way. The deep learning car has to process every pixel of every frame of video. It's brute force. A superposition-based AI could focus on the relevant objects and relationships, the things that are most likely to influence the outcome. It's more like a focus simulation than a comprehensive scan.
Okay, I'm starting to see the potential, but how do we actually implement this? What kind of algorithms or architectures would be capable of reasoning by superposition in a way that's more than just parallel processing in a neural network?
That's the million-dollar question, isn't it? One approach might be to combine deep learning with symbolic AI. Use deep learning to extract relevant features from the environment, and then use symbolic reasoning to manipulate those features and generate predictions.
I think that's a promising direction. We need to move beyond purely data-driven approaches and incorporate more explicit knowledge representation. Think about things like Bayesian networks, probabilistic programming, or even good old-fashioned logic. The key is to find ways to represent uncertainty and to reason about multiple possibilities simultaneously.
I think we also need to think about how the brain does it. How does the brain represent and manipulate spatiotemporal information? What are the neural mechanisms that underlie anticipation and planning? If we can understand those mechanisms, we might be able to translate them into algorithms.
And that's where the neurosymbolic approach really comes in, right? Trying to understand how the brain uses both statistical and symbolic processing to achieve intelligence. Maybe we need to look at how the brain creates hierarchical representations of information, how it abstracts away from the raw sensory data to create higher-level concepts.
The hierarchy is key. You don't want to be superposing everything at once. You want to start with the most relevant possibilities, and then gradually expand the scope as needed. It's like zooming in and out of a map. You start with the big picture, and then gradually focus on the details.
Exactly. And that hierarchical structure might also help us to deal with the computational complexity of superposition. If we can break down a complex problem into smaller, more manageable subproblems, we can superpose the possibilities for each subproblem separately, and then combine the results.
It's almost like a fractal approach to reasoning. You have the same basic reasoning process operating at different scales, different levels of abstraction. That could be a very powerful way to deal with the complexity of the real world.
Okay, let's bring this back to current AI. Where do you see the biggest gaps in current deep learning models that this superposition approach could potentially address?
I think the biggest gap is in common sense reasoning. Deep learning models are very good at recognizing patterns, but they often lack a deeper understanding of the world. They don't understand cause and effect, they don't understand physical laws, they don't understand human motivations.
Yes, and that lack of understanding makes them very brittle. They can easily be fooled by adversarial examples or by situations that are slightly different from what they've seen before. A superposition-based AI, with its ability to reason about multiple possibilities and to understand the underlying causes of events, would be much more robust.
And it would be more explainable. One of the biggest criticisms of deep learning is that it's a black box. It's very difficult to understand why a deep learning model makes a particular decision. A superposition-based AI, with its more explicit knowledge representation and its more transparent reasoning process, would be much easier to understand and debug.
So if we're moving towards this neurosymbolic approach, what are some of the biggest challenges we face?
One of the biggest challenges is bridging the gap between the statistical and symbolic worlds. How do we extract meaningful symbols from the raw sensory data? How do we combine those symbols in a way that's both efficient and robust? That's a very difficult problem.
And another challenge is dealing with uncertainty. The real world is full of uncertainty. How do we represent that uncertainty in our models? How do we reason about it? How do we make decisions in the face of it? That's something that current AI systems struggle with.
And then there's the spatiotemporal challenge. How do we represent and manipulate information about space and time? How do we track objects over time? How do we predict their future movements? That's something that requires a very sophisticated understanding of physics and geometry.
And finally, there's the challenge of scalability. How do we build AI systems that can reason about complex, real-world problems without becoming computationally intractable? How do we make sure that our superposition doesn't explode into an infinite number of possibilities?
Right. It's a fascinating area, but there are still so many open questions. We've talked a lot about the theory, but what about the practical applications? Where could we see this reasoning by superposition being used in the near future?
Well, I think we've already touched on a few examples. Self-driving cars are an obvious one, but I could also see it being used in robotics, in medical diagnosis, and financial analysis in any domain where you need to make decisions in the face of uncertainty and complexity.
Yeah, anywhere that requires anticipation and planning. Think about logistics and supply chain management. You need to anticipate potential disruptions, like weather events or factory closures, and plan accordingly. That's a perfect application for this kind of reasoning.
I'm also thinking about areas like cybersecurity. You need to anticipate potential attacks and defend against them. That requires a deep understanding of the attacker's motivations and capabilities, as well as the vulnerabilities of your own systems.
It's exciting to think about the possibilities, but we need to be realistic about the challenges. This is still a very early stage of research. We have a lot of work to do before we can build AI systems that truly reason by superposition.
Absolutely. So let's shift gears and think about future research directions. From my perspective, I'm really interested in exploring the connection between this concept of reasoning by superposition and the way the human brain works. I think understanding the neural mechanisms that underlie anticipation, planning, and decision-making could provide valuable insights for AI design. Specifically, I'd like to see more research into how different brain regions interact during complex thought processes. Areas like the prefrontal cortex, hippocampus, and thalamus seem to play crucial roles, and simulating their interconnectedness could be more fruitful than simply scaling up current deep learning models.
From my side, I'm fascinated by the potential of scaling current deep learning architectures, but I think we need to focus less on accuracy metrics and more on understanding the underlying principles that guide the design of these networks. I want to understand how context is retained across long sequences of data and how the sheer volume of data influences the resulting models. It's a bit of a black box right now. I'd love to see research that tries to trace the patterns of activation within neural networks as they're engaged in complex reasoning tasks. Quantifying the relationship between those activation patterns and emergent reasoning capabilities seems like a crucial step towards measuring progress toward AGI. It's not just about what the model does, but how it does it.
My focus would be on developing better neurosymbolic algorithms. I think we need to move beyond the idea that neural networks can magically discover all the hidden rules and structures in data. I want to see more research into architectures that explicitly represent knowledge and reason about it. I'm particularly interested in exploring how we can create hierarchical representations of information, abstracting away from the raw sensory data to create higher-level concepts. We need examples of neurosymbolic algorithms that can reason effectively about complex, real-world problems in a way that isn't just memorizing correlations. We also need to understand the computational limitations of these approaches.
I'm convinced that the key to AGI lies in understanding spatiotemporal reasoning. I want to see research that focuses on how AI can track things over time in multiple dimensions and how it can translate between different coordinate systems. If a core algorithm can effectively translate between these, it might allow for a more holistic understanding of complex spatiotemporal relationships, which seems crucial for AGI. I also think we need to move away from the focus on accuracy metrics and start delving into the underlying mechanisms. How can we trace the thought process and its spatial-temporal relationships? If it's truly an emergent property of this vast, interconnected system, then where does that emerge from?
Those are all fantastic points and excellent directions for future research. It's clear that reasoning by superposition is a complex and multifaceted concept, but one that holds tremendous potential for advancing the field of AI. It forces us to think beyond the limitations of current deep learning models and to explore new approaches that integrate neuroscience, symbolic AI, and spatiotemporal reasoning.
Absolutely. It's a challenging but incredibly rewarding area to be working in. The potential payoff, truly intelligent machines, is worth the effort.
I agree. Even if we don't achieve full AGI, the pursuit of this kind of reasoning could lead to significant breakthroughs in our understanding of intelligence itself.
And it could also lead to more robust, explainable, and trustworthy AI systems, which is something that's becoming increasingly important as AI becomes more integrated into our lives.
Well, that brings us to the end of our discussion. Thank you all for your insightful contributions, and thank you for listening to Cognitive Spirals. We hope you found this exploration of reasoning by superposition thought-provoking and inspiring. Join us next time as we continue to explore the frontiers of consciousness, cognition, and machine intelligence.